Okay, hello Physical Science, this is Mr. B, and we're going to wrap up section 1. Again, this video should be a little bit shorter. So if you remember from last video, we talked about the kinetic theory and how it explains the properties of a gas. And again, that was all it was initially designed for, so there's a lot more in-depth information about the kinetic theory and gases. However, we can use it to apply to liquids and solid as well. So that's what this video is going to take a look at, is how the kinetic theory can also apply to liquids and solids. So we're going to start with how it can explain the behavior of liquids. So it says the particles in liquids also have kinetic energy, which again, remember, is the energy of motion. So why does a liquid such as mercury have a definite volume at room temperature instead of expanding to fill its container? Because again, that's what a gas can do. It can expand to fill whatever container it is in. And remember, a liquid, it will take the shape of the container, but it's not going to expand and increase its volume to actually fill it up all the way. So the reason why why this happens is because the average speed of a mercury atom is much slower than the average speed of a helium atom at the same temperature. Because again, at room temperature, helium is a gas, and at room temperature, mercury is a liquid, so mercury is going to move much slower. So the particles in a liquid are more closely packed than the particles in a gas. Therefore, attractions between the particles in a liquid do affect the movement of the particles. So again, this is going back to the fact that liquids are kind of in a random array, but not nearly as random as it is in gases. So because these particles are so close to one another, there is an attraction between them. They're actually bonding to one another. They're actually kind of holding each other in check a little bit. Again, whereas a gas, they're so far apart, they're moving it so fast that there is no attraction there. So therefore, attractions between the particles in a liquid do affect the movement of the particles. So because, again, the fact that there does exist an attraction between them, then some of that mercury is not just going to be able to expand and go away from the other particles to fill the volume of the container. They're kind of stuck, again, to keeping that definite volume there. So they give us kind of a little example here that a mercury atom in liquid can be compared to a student in a crowded hallway. So the student's path may be blocked by students moving in the other direction, and the student's ability to move is affected by its interactions with other students. So again, if we change this student and said maybe this guy right here in the middle, if he is a mercury atom, a liquid mercury atom, again, he can still move. However, he's not going to be able to move too fast because, again, he's going to run right into this girl in front of him. And again, maybe someone else is going to run into him that's going to keep him from moving too much. So again, he'll eventually be able to move. Again, he's not stuck in one place necessarily, but his movement is limited by the fact that there are other students interacting with him and there's other students that are blocking him from moving as well. So that is, again, why liquids don't really necessarily behave in the exact same manner that a gas does, because there are, again, more interactions taking place here. So it says, again, just to kind of re-emphasize this, is that a liquid takes the shape of its container because particles in a liquid can flow to new locations. Again, that student eventually will move to a new location, so that is why the particles in a liquid will fill their container. However, the volume of the liquid is constant because forces of attraction keep the particles close together. So again, the liquid, it can take the shape, but it's not going to expand to fill the volume because there are forces of attraction there holding the particles closer together. And again, in a liquid, there is a kind of tug of war between the constant motion of particles and the attraction among particles. So this tug of war explains the general behavior of liquids. So what it's saying is again, they're not in a completely orderly arrangement. They are kind of random, so they can move a little bit. However, there's a force of attraction saying, hold on, you can't go too far here, we're going to keep you kind of close here. So there's a kind of tug of war that kind of going on back and forth, like, yeah, we're random, no, we have attractions here. So they kind of keep each other balanced out, and that's what keeps them, again, from having the same characteristics of a gas. And because, again, the forces of attractions limit the motion of particles in a liquid, the particles in a liquid cannot spread out and fill a container. So again, they can take the shape of a container, but they will not expand to fill it up completely. And so now we're going to take a look at, to wrap this up, how this can apply to solids. So solids have a definite volume and shape because particles in a solid vibrate around fixed locations. So when we think of a solid, we think that there's no movement whatsoever. The particles are stuck in one spot. However, that's not necessarily the case. When we look at solids at, again, the atomic level, we kind of know that they're vibrating, they are moving slightly around fixed locations. So vibration, again, hopefully we might be able to kind of infer what this might mean, is a repetitive back and forth motion. So again, maybe you could say now my mouse is vibrating because it's moving back and forth like that. And so to give our example, we think about the atoms in solid copper. So strong attractions among the copper atoms restrict their motion and keep each atom in a fixed location relative to its neighbors. So again, in the gas, there is no attraction amongst the particles because it's so random. A liquid, there is some attraction because they're not quite as random in a gas. And when we get to a solid, the arrangement is really orderly, it's really compact, so there's very strong attraction between each atom and their neighbors. And so each atom is able to vibrate around its location, but it does not exchange places with a neighboring atom. So there is some motion going on in there. However, it is not going to actually flip-flop and change spots because, again, they cannot, because they have such strong attraction among each particle. And to wrap it up, it says, to explain the behavior of solids, it says you might compare the particles in a solid to a polite audience in a movie theater. So again, that's the key thing here, because this one, I've been to some movie theaters where this will not apply when we think of a polite audience in a movie theater. So although people move around in their seats, each person remains in essentially the same location during the movie. So my example is sometimes I put my feet up on the seat in front of me, sometimes I stretch my legs, sometimes I put my legs underneath, sometimes I shift a little bit. So I am moving in my own seat. Again, I don't keep, and sometimes I reach for popcorn, sometimes I reach for my drink. So again, I'm not necessarily staying in my exact same spot the entire time. I'm moving a little bit. However, I have a fixed location in the fact that I am staying in my seat, but they compare the vibration to moving around in your seat. So they have fixed locations in a total volume that does not change. So that is kind of how a solid works. Again, they vibrate around, but again, since there's such strong forces of attraction existing there, they're not going to necessarily go from place to place. So that is it for section 1. Let me know if you have any questions.